So just, there are some people told me that they were not here last time and that the video was not very clear. So let me very briefly recap what we have seen last time. So the idea was to make some examples of some behaviors, so say of mathematical objects that are universal. So like many different problems behave in some limit or some regime in the same way. And, but in some special cases are explicitly computable. So this limit or this regime. So if we can like compute it in one special case and then claim that it's universal for many other cases, we computed at least the limit explicitly for like a universal class, it's called, okay? So and the example was like linear operators in E infinite of very high dimension. And the idea is that, okay, this is just very, very informal, sorry, here it's not visible, very, very informal, is that in certain regimes, a lot of linear operators, they just behave as a very large matrix. And what kind of matrix? Like a matrix, random matrix. And so we were looking at eigenvalues of very large matrix, how do they behave? And in particular, of course, it depends what numbers you write in the matrix. So the idea is that this behavior is somehow universal if you put in these numbers randomly, okay? So we made like a large matrix n by n by n, and here we would put random variables that depend on n, x and n. I put an n here to claim that they depend on n, okay, also 1, 1 depends on n in its law, okay, and we did take Eij n equal to Eji. This is so that the matrix is symmetric. Of course, you can also just take them all independent, and the description will be slightly different, but this is also a solved problem when when the entries are all independent and not like independent up to the fact that they are symmetric on the diagonal. And this was equal to 1 over square root of n some Yij, if I was, say, bigger than j. So, of course, and then when j is bigger than I, it's just here. And 1 over square root of n some zi, when I is equal to j, where the Yij, Zij were all independent. So the y's are independent from the j and among them, okay? All these are all independent random variables. And so the y, they have all the same law of a given random variable, and the zi, they all have the same law of a given random variable z. So this just means that the yi are independent, identically distributed. The zi are independent, identically distributed, but maybe that the distribution of the y and of the z is different. And then we had assumed that the expected value of y square was, so the expected value of y was 0, and also the expected value of z was 0, and the expected value of y square was 1, the expected value of z square was, okay, finite. And then we defined what's called the semicircle law. Okay, why this square root of n? Just because it's the right number to have a limit, okay? Otherwise, what we are looking at will not have a limit. Then we defined sigma, which is, this is a probability measure on R, Borel probability measure on R. So sigma is just the probability measure with density given by 1 over 2 pi square root of 4 minus x squared, provided that x is less than 2. So it's just dx. So it's just the measure with a circle as, so between minus 2 and 2, circle of half circle. So this is the density, and this is, it's clear what it means, a probability measure with this density. I should stand here because otherwise it's not visible. The probability measure with this density, yes? Yes, okay. So this means that sigma of f, which is just a short notation for the integral, means is times this density. Okay, and then this is a given probability measure, no randomness, is this probability measure. And then for each n, we had this big matrix with these entries. This is symmetric, so it has n real eigenvalues if counted with their multiplicity. Okay? And so we made a random probability measure, pi n. Okay? This pi n depends on this vector x, on this matrix entries x. Okay? So it's random. And this was 1 over n, the sum from 1 to n of delta over lambda I. These lambda I are functions of this x and are the n eigenvalues of the matrix with entries xij. Okay, so this is random, okay? This probability measure depends on x. This just means that pi n now of f is 1 over n, the sum of f of lambda I. This probability measure. So what we are, and we wanted to prove a theorem.
But is n just a normalized trace, or is it something else?
No, it's a probability measure. So let me write it. Let me write the theorem and let me tell what it means. Okay. So the theorem was that the probability that the limit when n goes to infinity of pi n is equal to sigma is 1. So sigma is this probability measure. I thought I had the colored chalks at home and I didn't find, sorry. So this is like this. And for each n, we have n real eigenvalues. So we put a small mass of weight n on these and the points where there is an eigenvalue. Okay? So like, I don't know, there is an eigenvalue here, an eigenvalue here, an eigenvalue here, an eigenvalue here. This maybe is double, so here there will be weight 2 over n and an eigenvalue here. Okay? And then n becomes bigger and bigger. So these little points, okay, the idea is that these little points, when n becomes bigger and bigger, they are like, I don't know, a sand that in the limit converts to a continuous limit. Okay? So this just means, so this is the probability measure. This is when you integrate it against a function. And these statements, if you put the right topology on probability measure, just means that for each bounded and continuous function on R, 1 over n, the sum of f of lambda I, this number is random. It depends on the entries, x1, 1, x1, 2, so it's random. Okay, so there is a probability that could be something, a probability could be something else. But with probability 1, when n goes to infinity, it converges to the integral of f of x in this sigma of x. So this sigma of x. So that integral there. Okay. So this object is the probability measure that puts a mass 1 over n on the point. So say this is the probability measure such that the probability that of the point where there is an eigenvalue is 1 over n. We have n points, so it's a probability. So it's a formal. This is a Dirac mass, yes. So this is the probability all concentrated on the point lambda I. So it's like according to this probability, the only outcome is always lambda I with probability 1. But then we like make a convex combination 1 over n the sum. So each of these points is probability 1 over n. When n goes to infinity, they become like denser and denser, and the theorem says that they converge to this semicircle. Okay? So if you have comments online, feel free to, I hope the audio, to ask. Yeah, the audio, it's on, so, okay. Good. Actually, we put this theorem like this, as I recall last time, it's very hard, and but in some sense, it becomes much simpler if we assume some comfortable hypothesis. And the comfortable hypothesis were that the expected value of y to the k is finite for every k. So we assume the 1 for k equal 2, and that's the hard part is to go from k, like assuming that this is finite for every k bigger than 4 to k just 2. But we will assume that for any k, it's finite, okay? Because this is a random variable, could be infinite. And the same for z. And also here, I said we proved a slightly weaker statement, but this part it would be easy to make from convergence in probability to convergence with probability 1. So we prove something slightly weaker, namely that the probability, so that pi n of f minus sigma of f is bigger than epsilon. This limit goes to 0 for every epsilon strictly positive. Okay, so this is so and for every, of course, for every function which is continuous and bounded. Actually, also for every function with this is the same for every continuous function with at most polynomial growth. So, so this statement is actually weaker than this statement because this is like this random number, the integral of f in d pi n, so this sum, this is a random number. We are saying that for every f, this random number converges in probability to this number. And here we are saying that it converges almost surely. So this is stronger than this. But going from this to this is easy. Just I don't want to spend too much time on it. Going from this hypothesis to the one here, that it was just the expected value of y squared was 1 and z squared was finite, this is much harder, and we don't check it.
Does this theorem have a name?
It's called, yeah, the Semicircle Law. So these originally, if they were Gaussian random variable, was proved by Wigner. And there were a lot of improvements. As I mentioned last time, the last one with k equal 2 was by Van Wu and Tao. And it's one of the celebrated results of Terence Tao. I do not know how to prove this theorem for k equal 2. So in the form that is stated. So we had checked last time that it's enough. So we can introduce the moment. So mk, this is the integral of x to the k in the sigma of x. Okay, so just x squared, square root of 2. And these numbers, they are actually, so this is equal to 0 if k is odd by symmetry. Okay. But is equal to ck over 2 if k is even, where ck is the Catalan number. So it's 2k factorial divided by k factorial times k plus 1 factorial. And we have checked that this is also the number of Bernoulli paths from 0 to 0. So this means the number of paths of length 2k. So we start in 0, 1, 2, 3, 2k. Okay. At every step, I can go up by 1 or down by 1. So for instance, up by 1, down by 1, down by 1, down by 1, up by 1, up by 1. And pass from 0 to 0, staying positive. Staying positive. So we counted how many paths go from here to here, never going below 0. So for instance, this. Okay, this is okay. I never went below 0. Okay, we counted last time, and there are exactly this many number of paths every time going up or down, and going from 0 and finishing in 0. We had counted also generating functions and so on, but okay. And given this, we also checked that these two lemmas were enough to prove this theorem. So lemma 1, it was that the expected value of pi n of the function x to the k, the limit when n goes to infinity, converges to mk. Okay, so this just means 1 over n sum from 1 to n of lambda I to the k, okay, for every k. So this is just this is random. This number is a random number. We take its expected value. It's just a real number, okay, and its limit is this Catalan number. That's the first lemma. And second lemma was that the limit when n goes to infinity of the probability that phi n of xk, so this random number, minus its expected value, x to the power k, is bigger than epsilon, this limit is 0. Okay? Why these two lemma, so why lemma 1 and lemma 2 imply the theorem in this form? Because if we have a function on a compact set, we can approximate it uniformly with the polynomial. If we, so it's enough to know this limit, this improbability for functions that are polynomials. Because we proved that the probability to be out of a compact set is very, very small. So it's enough to approximate uniformly a compact set. First step. Second step, okay, once we know it for polynomials, it's enough to know it for each power, because this is an integral, so they are linear, okay? If the sum of the probability that k things is bigger than epsilon goes to 0 for every epsilon, it's enough to know this, it's enough that each of these k things go to 0, so in probability, so that's okay. And so to know it so we need to know these things only for functions that are powers of x. And for powers of x, we divide this thing in two steps. One is that the random number average of the power of x, so this random number for each k, is close to its expected value in probability. And the second step is that the expected value is close to the Catalan number. Okay, so once we know it for powers, we know it for everything. Here it's, of course, as you understand, here it's very comfortable to have assumed this, because I mean, if this will not be true, it starts to be very hard to compute all the powers of an eigenvalue. This, of course, the powers of the eigenvalues are related to powers of the entries. So I can erase this, if this is clear. And and then we check that this, that's maybe to answer your question, is just 1 over n, the expected value of the trace of the matrix x to the power k, because the sum of the eigenvalues to the k is just the trace of the k power of the matrix. So using this fact, we had given a combinatorial representation of this random number. And here there was 1 to the n to k over 2. So yeah, okay, let's write this, k over 2 plus 1. So this plus 1 came from this 1 over n. And this k over 2 comes from the fact that here there is a power k, but each random variable was divided by square root of n, so there is a k over 2. And then there was a sum, so over all the sizes, let me briefly recall this, of, here there was n factorial divided by n minus s factorial, and then there was the sum over all the words in the space of words with length k and size n of the expected value of this random variable y to this expected value. Oh, there is a product, sorry. So product over all the edges in V. So let me write the formula and let me recall it, what it means after that. So here there was y to the n e w. We had called this connecting edges, and I had called this loop edges. Where, okay, these are just numbers. So what is this? What is a word? Okay, with so w, k, s. They are sequences of this type: I1, I2, ik. So k is this number, and then they finish in I1. Okay, such that s different. So with I1. Ik, yeah, okay, where they are symbols, okay, and exactly, so let's try this. I1, Ik are in 1s, okay, this s, and all the symbols 1, S are used in the word, are used in I1, Ik. So S is the minimal number for which you can represent this, okay? If you use, or if this is just 1, 1, 1, 1, 1, 1, 1, you would take S equal 1, okay? Not 2. It's, okay, it's the minimal number. And they were, so they are closed. And we had make a quotient with respect to, like we said, the two words were equivalent if you can map ones in another, just changing the names of each letters in this alphabet. This means that so the quotient just means that here the first symbol that appears is 1, okay, because that's like we choose this representative, for instance. The first symbol that appears is 1, then maybe there are a few ones, I don't know, but then the second symbol that appears could be I2, could be another one, I will call it 2, okay? And then, okay, maybe there are some 1s and 2, but the third symbol that appears, I will call it 3, and so on. So, like, are the words like this where you never see a 2 before a 1, a 3 before a 2, and so on, up to S, okay? So, how to get this, we just made the expected value of the trace and used a bit of combinatorial. Actually, this factor here is just how many words without this identification there are in each equivalent class. Equivalence class. So to make this formula, you just write the trace and make all the things. Now, if we have such a word, what we do, it's important to finish the computation. We make a graph, okay, with S points. So to such a word here, there is associated a graph. This graph has as vertices these n points, 1, 2, 3 up to S. 1, 2, 3, 4, S. S. And then we call EW the set of edges in the graph that are built in the following way. If two symbols are adjacent in the word, we draw a line between them. So for instance, if I have 1, 1, 2, 1, 3, 4, 1, okay? So here we have K, this is a word where in W, 1, 2, 3, 4, 5, 6, the next is just to make it close, the 6, maybe I can write it here, this is a word in W, 6, 4, yeah, because the length is 6 plus 1 and there are 4 symbols that I used. So here 1 is connected with 1, then 1 is connected with 2, 2 is connected with 1 is already there, 1 is connected with 3, 3 is connected with 4, and 4 is connected with 1. And that's how I made a graph, okay? And ECW is the set of connecting edges. So the edges connecting two different vertices. So for instance, this is a connecting edge, this is a connecting edge, this is a connecting edge, this is a connecting edge. And EWL is the set of loop edges. So in this case, only this one. Okay? And NEW is the number of times my word passes through the edges E. So for instance, this word has, for this guy there is the NE, this edge is 1. For this edge here, there is 1, 2, but there is also 2, 1. So here the number of times I cross this edge is 2. Okay. Then 3, 4 is 1, then the others are just 1. For 1 is 1, and on this edge this number is 1. Okay. Why does it appear? Because when you write the trace, every time there is x1, 2, x, like every time when you write the explicit expression for the trace, how many times there is, I don't know, entry x1, 2 to some number of, to the power, every time there is power 1, so you get the expected value. Since all the entries are independent, when you take the expected value, it's just the product of the expected value, but they're independent unless, like xij and xi prime j prime, they're independent unless ij is equal to ij prime or to j prime I prime. So that's how we came to this expression, yeah, because I had to write something like x I1, I2, x I2, I3, and so on, x ik, I1, sum over I1, ik from 1 to n, to make this will be this sum will be the trace of the matrix x to the power k. So if I put together all the xij with the same index, when I take the expectation, I come up to this expression, okay? And okay, then we computed the limit of these things. So the limit, when n goes to infinity, of the expected value of pi n of x to the power k. So this is what it was. So we have checked that this guy doesn't depend on n, what is on the right, only depends on k and s. So that's why we use these minimal symbols, because otherwise this guy would go from 1 to n, but we have checked that we can stop at 1 plus k over 2 with this. Otherwise, some expected value will be 0. And here, this number that depends on n goes to 0 unless s is exactly k over 2 plus 1. So this means that this was 0 if k is odd, because due to this integer part, s will never be 1 plus k over 2. So this factor will always count. And if k is even, all this factor in here for this value of s will go to 1 actually. And so here the only thing that matters is the sum of all the words in W k over 2 of the product. Of these expected values that are there. Okay, this. However, I had left however, what we noticed here immediately, and then there was a little exercise I left that we are going to review today. So you see, every time E and EW is 1 or say is 1, less than 1 cannot be because that's the set of edges, so is 1, this is 0 because the expected value of all these random variables was 0. Okay, so this counts. So each word. So in this sum, the only words that count are those that pass at least twice on each edge. Because if they pass only once, there will be an edge for which this is 0, and then all the product is 0. Okay. So I have to count so I only have to count the words that are closed, have length k plus 1, and use exactly k over 2 symbols. Okay. And for this, I have this thing, NEW, Z, NEW, product over all the edges. But now, look, so I have a graph. Okay, it has k over 2 symbols. K is vertices. K is even. Okay, k over 2 symbols. And I have a path of length. So with that visit k plus 1 vertices. So it has it crosses k edges. Okay, and these k edges, it crosses each of them at least twice. But I have k edges to cross. I have to visit k over 2 symbols. I only have one option, that each edge I visited exactly twice. Okay, because otherwise I could not connect k over 2 symbols. So this means that so either this is 0, or if it is not 0, this NEW is exactly 2. So if this is 2, okay, it's exactly 2. That's the first thing. The other thing we have seen is that on these words that count, there are not loop edges. So, okay, let's make a more general statement. That was the exercise I left last time, which is the following. So if we have a word like this that passes on each edge at least twice, so actually exactly twice, then this graph that we built from the word is a tree. I left this exercise. So we have k vertices. So, okay, k vertices. And we have a path that draws k edges and connects them all. So this path connects them all, because in this word I connected all the two symbols if they were adjacent in the word, consecutive in the word, but I drew only the points that the word visits. So the first point is connected to the second, then when number 2 appears, it will be connected so 3 will be connected to 1 and to 2, 4 will be connected to 1, to 2, and to 3, and so on. So the graph is connected by this path, okay? And so it's a path with k over 2. It's a connected graph with the k over 2 vertices, yes. So the number of edges, and so the number of edges is at least what? K over 2 minus 1. So the number of edges is at least k over 2 minus 1. Why there is minus 1? Yeah, because if I have a connected graph with k over 2 vertices, since it's connected, there must be at least k over 2 minus 1 edges. Sorry, what am I saying? There are k, yeah, that's, sorry, that's why I'm saying something. So there are k no. Yeah, length, yes. So there is minus 1. So no less, sorry, no less than minus 1. But I want to claim also that there can be no more than k2 minus 1 edges. Why? Because if I had, let's see, so if I have like 1, 2, 3, 4, 5, and k, that's what it was, yes, k over 2. Let's see. So every time I visit an edge, I have to visit it. Okay, it's trivial, just because the length of the word was k plus 1. So I'm doing something, yes. The length of the word was k plus 1, and the last entry was closed. Okay, the last entry was equal to the first one. So I have just k plus k, exactly k times. I have it like k times to cross edges. Okay, my word cross k times these edges, and if I have to cross each edge at least twice, I cannot draw more than k over 2. Actually, k over 2 edges. I cannot draw more than k over 2 edges. So I have a problem here with this minus 1. So why cannot it be k over 2? No, but I have to cross k edges.
No, I guess that the problem was in the first one. So is it true that you have exactly double k over 2? Maybe.
Oh, that's why I have k over 2 plus 1. Sorry, S was k over 2 plus 1. That's why. So yeah, thanks a lot. Thanks a lot. Yes. So here there is plus 1. Okay, sorry. Yeah, thank you. That's if you remember, S the only term in the sum that has that matter was 1 plus k over 2. That's why. Thanks a lot. So if I have k divided by 2 plus 1 vertices, I need to, and the graph is connected, I need to have at least k over 2 edges. So we are just looking at the fact the exercise of last time that that wk k over 2 plus 1 was a 3. And since there is a word, so there is a path that visits all edges at least twice, connects the group, spans all the vertices, and has length k plus 1, and visit k plus 1 depth, so it crosses k edges, the number of edges cannot be more than k over 2. So if you have a graph with a certain number of vertices, say k over 2 plus 1, and the number of edges, which is exactly the number of vertices minus 1, this is a tree, okay? Because this is the minimal number of edges that, like from this inequality, is the minimal number of edges that can connect to the graph. So if you have a loop, you can remove one edge and it's still connected. So there cannot be any edge on this graph. Such a graph is called a tree. So these words in here, they are done like this. There are k over 2 plus 1 symbols, okay? But all the graph, it's a tree, okay? And the path that is represented by this word is something like this. You start in some point, you go somewhere, then tack, tack, back, here, and back to the origin, okay? This is the graph, and I drove the path, okay? I draw it a bit detached, but you really, so I go here, then here, then here, then back, then here, then back, then here, then here, then here, then here, then here, then here. Usually this is described like this kind of combinatorial problems as the path of like an insect that walks over the tree, okay? You really have a tree, and the insect starts here, it tries to go up, and when it cannot go up anymore, it comes back and then visits all the branches, okay? Until it comes back to the origin. That's the only way, like all the other words in this computation of the trace of x to the k didn't matter in the limit when n goes to infinity, only the words that are done like this, okay? So for instance, I don't know, 1, 2, so for instance, if this is 1, 2, 3, 4, 5, and 6, okay, that's all this 1, 2, 3, 4, 5, and 6. The word that represents this tree is just this path 1, 2, 3, 2, 4, 5, and 6, okay. So and 1 again, and 1 again. So once I do this, you see that, so in particular, we see that there are no loop edges, otherwise it cannot be a tree. So this product over loop edges is empty, is 1, okay? And all the connecting edges in the graph, they have order here too, are visited by the path exactly twice by this description. So this is just 1 every time. Okay, so this limit is nothing but the cardinality of this space. Let's put a little dot to remember that also each word passed each edge exactly once. So to compute this limit, I just have to compute the amount of trees of this type. Okay, so with a word like this. But this is exactly, my claim is that this is exactly the Catalan number. And why? Let me build a simple bijection between this kind of trees with this kind of path and a Bernoulli walk that stays positive, okay? It's very simple, of length to k, okay? So you give me a tree with k over 2 plus 1 edges, okay? And this path that visits started, and if you remember, we had numbered, like the first guy I visit is 1, the second is 2, the third I visit is 3, then okay, maybe I visit again 1 or 2, but then 4 and so on. So if you give me this tree, how I make a path here that stays positive, okay? So I start from 1, then I go to 2 on the path, so I visit a new branch, okay? So I go up. In this graph here, I go up. 1, 2, 3, so here will be actually 10, yes? K plus over 2 plus 1 was 6. Then I visit a new branch and go to 3. So I go up again because it's a new branch that my path here visits. But then I go down to 2. I come back on the same branch I visited. My insect that is walking already passed on this branch and comes back. So here I go down because I come back. Then I go to 4, okay? So it's the first time I visit this, I go up to here. Then 5, I go up again. Then, okay, this is not 10, I'm making the lines too long, but then I come back and then up again. And then I always go down. I visit. Okay, and that's the path. So that's how I build this tree from this path. Conversely, if you give me this path, that's how I build the tree. Every time I go up, I open a new branch, and when I go down, I come down on the last branch. So, for instance, on this path, let's try. I start from 1, I go up, so I create a new branch. Then I go up again, I create a new branch. But then, so if you want, I build the word. It's the same thing. I build the word here. So, but then I have to go back. Okay, by 1, so I pass back on the same thing. So if you want, the word was, I was in 1, I visited 2, then here there is 3. So it's 1, 2, 3. Then I go back to 2 because it was down. So 2, then up. So once I'm in 2, if it was down, I would go back to 1. But no, I open a new branch because it's up. And then once I'm here, I open again a new branch. Then down, so back to this. Then up, a new branch, and then all down. So it's 1, 2, 3, again 2, then this is new 4, 5, 4, 5, back to 4, 6, and then back to 4 to 1. Okay? So this is a bijection because how I built one from the other is exactly like if you apply this twice, of course you come back to the original tree. So that's it. So this is CK because we have counted that the number of these paths that stay positive is exactly CK. Okay. So this was the first lemma. And the second lemma was that the second lemma, we will not compute it because they say once we have this, we understood where does this semicircle come from. Just because, okay, it's a bit of a miracle if you want, then that one can say one calculates explicitly all the limits of the k moment of this random distribution, okay, and finds these Catalan numbers. Then there is a bit of a miracle that one can write explicitly a probability measure, this one, that have as a k moment these Catalan numbers. Oh, CK odd 2. I erased it, I think. We had already checked then if k is odd, this limit was 0, as for sigma k, and when k is even, this is CK over 2. So as in sigma k. So as in sigma k. Yes. Yeah, the length of the path was actually k. Root 2k was actually k. So good, and so the fact that we find explicit the probability measure with this with the density such that it's k moments, the integral of x to the k is exactly this, is a bit of a miracle. But in reality, last time I mentioned it, that there is a reason for this, is that if I didn't take the symmetry on this random variable, I would have got complex eigenvalues, and so if I would have made the same measure, but on C, the limit would have converged to a circle of radius 2 in C. Okay, like a probability measure which has a density constant along the circle and 0 outside. So then it's a corollary of this fact that if you take the symmetric part of this matrix, then you would get as a spectrum just the projection of this measure on the real axis, and of course the density will like if you have some material uniformly distributed on a circle and then you just smash it on a line, of course the density will be like this along that line. Yes. So that's just a corollary of this very nice picture. But in reality, at the same time, it's a bit of combinatorically, you just compute this number, and then there is a little kind of analytical miracle that you can write analytically this probability. Okay, otherwise you have to otherwise this would be a probability with these moments, and you say the fact that it writes explicitly is a sort of a miracle. But then we should have also checked that. But I don't want to do it because we don't have enough time. This statement, yes, that the probability that pi n of xk minus its expected value goes to 0, x power k. So it goes to 0 in probability, so that the probability that is bigger than epsilon goes to 0 for every epsilon. This probability is how to prove this lemma 2 was. Let me just give a sketch of the proof. For lemma 2, this is one way to compute it is just to say that you use Chebyshev inequality. So this is no more, yes, than 1 over epsilon square, the expected value of the square of this thing. So it's pi n of x to the k minus the expected value of pi n of x to the k, and here I should do this squared, okay? But this squared, yeah, it's like if you do the double product, it's like for variance of random variable. This is exactly the expected value of this variable squared minus the expected value of this squared. And we have to compute and we have to check just that the limit when n goes to infinity of this guy is 0. This you already know that's go to c k over 2 squared. But so in reality, okay, we can just keep like this, it's better. And now here, you can write, as we wrote the expected value of pi n to the xk as a sum over all the words, here we can write the expected value of pi n of xk squared. So this is a probability measure. This is the probability measure. You integrate x to the power k with respect to the probability measure. This is still random. You square it and you take the expected value. So this is not pi n x to the 2k. Yeah, it's smaller actually. So this 2 is here, not here. So instead of writing as a sum over all the words as we wrote there, you write as a sum over all couple of words. And these sometimes are called like phrases, but here they're just, to compute these with a combinatorial expansion, you just need to use phrases of 2 words. And then all these things rise nicely in the same way, and you just check that the limit is 0. I don't compute it because here you have to, in the previous, we had to really find the number. And here we don't have to find it. We just have to say that it's small when n goes to infinity. So it's like the same computation as before, but all the terms, we have checked that all the terms mattered except the one with size k over 2 plus 1. And here you just check that no size matters. So the limit is 0 in the limit when n goes to infinity. So it's very similar computation, so we drop it, okay? And this was just an example of something. So now I say that there are some problems that are like universal, and you want to prove universalities, and some problems that are like computable explicitly, and you want to compute. It was an example, but in reality, you can view it as both. On one hand, you want to claim that, I don't know, a matrix with random entries has a spectral feature similar to many linear operators. And so, and then here, at least this quantity we can compute explicitly, for instance. So this is sort of something computable. At the same time, we also prove that no matter what is the distribution of each entry, you always get the same limit. So it's also some universality, yes? The limit of the eigenvalues, they do not depend on how you chose these independent random variables. So there is a sort of also universality. So it's an example in both words. Of course, the very universal claim, nobody knows what it really means. What does it mean that linear operators behave the same way? It's just, I don't know, some ideas. I don't know, for instance, some Schrödinger operator with generic potential, if you look at high spectrum, could have something looking like this in some dimensions and so on. It's some informal ideas, say. I would also, so just for the next, here I took, so what is on the diagonal doesn't matter, if you remember. the expected value on the diagonal doesn't matter, of the square. Of course, you need to take that the expected value on the diagonal is 0, because if it would be 5, this would just shift by 5 all the eigenvalues. So this is 0, but the expected value of z square, it didn't matter, okay? But if I change the expected value of y square not to 1, but to some number t, okay, positive, what would happen to the eigenvalues? The eigenvalues, so this, okay, I can also change it z square by t, so there would just be square root of t, the eigenvalues of a matrix, square root of each eigenvalue of this matrix where variance of each entry is t, would be square root of t, the eigenvalues of the matrix with the variance 1. Okay, so this matrix, this measure for this matrix, delta, okay, the eigenvalues will be t, lambda n, t lambda I, okay, where now these are the these are the eigenvalues of this matrix, where this matrix where the lambda I are eigenvalues of a matrix with entries with variance 1, just by dividing y by t. So this means that 1 over n. So if I look at this measure, so at this measure, okay, pi n, okay. So I don't know to what does it converge now, okay? To what probability measure does it converge? I know these are now eigenvalues with associated to a matrix with variance 1. So when I do, I don't know, for instance, 1 to n, a function of these eigenvalues, this is just square root of t lambda I. So this just converges to sigma, this sigma of x, to f of square root of tx, this sigma of x. So I can write this as the integral of some f of x, let's call it sigma t of x. If I choose sigma t of x, 1 over 2 pi t probably, square root of 2 minus x square of t, provided x square is x is less than 2t. No, 4. This was 4. Sorry. X is less than 2 square root of t. So, if t is very small, of course, I still see a circle, but just from minus 2 square root of t to 2 square root of t. And this is just this probability is normalized. I mean, if you make a change of variable, I hope I put the t in the right place. It seems so. Is it clear? So the variance is very little. The limit would be a small circle or constant around 0. Then if t is big, yes, okay. So this, let's keep it in mind. And now I want to, in some sense, not completely change the subject, but ask similar questions when I take, again, a very big matrix, but on each place there is not, so here we just look at each entry we put an independent random variables. And now I still want to put something independent, but like different mathematical objects, not real numbers. And in particular, a very classical case due to Dyson is I put here some function, okay? So as a function here, I mean like an element of a Banach space, continuous functions with values in Rd, or let's say R. Okay, so in each entry will be just a function of t. Okay, it's a function. The simplest case is, of course, it's just a function of a real variable, but a random function, like random. Before we had random numbers, now I put random functions. Okay, so a random function is basically a stochastic process. Have you ever heard about like stochastic processes, Brownian motions, these kind of things? No? Okay, we will need very little of stochastics. It will be more, again, a bit of, say, integrability properties, like before, some magic things that appears neatly more than the stochastic part, but we need a bit of preliminaries about it just to get an idea of what we are writing in here, okay? So, in particular, the most classical case is when one here puts independent Brownian motions. So, B11 of t, B1n of t, Bnn of t, and so on. So, like for each...
Does this problem come from somewhere, or is it just an idea?
This is... so, yeah, okay, let me explain. Right. I tell you, I say it in a moment, okay? So, yeah, we are quite right. So, why am I doing this? Okay, let me give at least one motivation, okay? Right, sorry. I wanted to discuss this briefly and I just forgot. So what is the idea? In the previous computation, we have just a lot of random variables, okay? And we computed this average of the limit of this measure when we put mass 1 over n over each eigenvalue. Good, but this description is not very detailed. Indeed, you see it's universal, it's the same for every random variable. So, for instance, it doesn't tell me anything about a single eigenvalue. What does it do? A very classical example is the largest eigenvalue. Yes, this matrix, okay, will have a largest eigenvalue, maybe with some multiplicity, but largest eigenvalue. But here it only counts with 1 over n, this eigenvalue, the largest one. So when I have to do, if you tell me what is the limit of 1 over n f of lambda I, okay, but I know the largest one. Even if I know this limit, I don't know anything about the largest eigenvalue because the largest eigenvalue could go to infinity. This function says bounded. It could go to infinity, it could go to 0, it could go to 0, no, because it's concentrated between minus 2 and 2. But it goes to 2. Maybe it goes to 2, maybe it goes to plus infinity. Or maybe it oscillates between the two in the limit when it goes to infinity. I don't know. If I do, anything is possible in this when I take n to infinity. This limit doesn't tell me anything about, I don't know, the largest or maybe the 5 largest eigenvalue, 1, 2, 3, 4, 5. Any finite number or even a fraction, negligible fraction of n of eigenvalues are not described in this limit. But this is a very typical interesting question, like behavior of high eigenvalues, like the largest, the second, and so on. And they also are supposed to feature a universal behavior in some sense. So, so actually the largest eigenvalue here, it goes to 2, which is not obvious because like you have a fraction n, a good fraction of eigenvalues concentrated between 2 and 2 minus epsilon. A good fraction means a non-negligible fraction of n. Yes, that's what the previous result tells us. But it could be that a few of them, you know, get dispersed to infinity, for instance. And that's not the case. Actually, the largest one really converges to 2, for instance. And so this is not the only motivation why I want to do this a bit weird generalization. Well, first in general, you can imagine that, okay, taking eigenvalues and of a matrix, I don't know, it makes sense in fields that are not just real numbers. So I don't know, I can just, on a purely algebraic point of view, consider like this kind of structure for different random objects. But also, as we will see in a moment, we will have a very interesting and clear description of the eigenvalues of this guy if I put here Brownian motions, very special random functions here. And this will allow us to compute to get a very precise idea of how these sort of eigenvalue interact between them. We will see that they sort of repel each other. So if there is an eigenvalue here, it decreases the probability for fixed n that there are other eigenvalues around it. Okay, it keeps an outside. And there is a very famous mean field description of the system in this case, which also extends to other cases of more general linear operators. So more general matrices, not with independent entries, for instance. And so it's called a Dazen Brownian motion, and a certain field of mathematics has been a very influential example. There is a whole world what's called like beta ensembles and so on that started from this example. And it's a quite active field of research. This is quite far from what I do in my life. I'm not an expert at all in this field, but for instance, on beta ensembles, there are some very famous mathematicians working on it, like of course, Alice Guionnet, who wrote several notes and so on about this, and you can find her. But there is also Sylvie Serfati, who is a sort of real star mathematician in France and NYU. And also, I don't know, latest Fields medalist Figalli, he wrote about beta ensemble and so on. So it's a pretty active field of research and very well reputed. If you know a bit about Gibbs measure and so on, there is a bit of that. But so since here we do like real symmetric random variables, is like temperature 1. But so beta ensemble, we will take beta ensemble with beta equal 1, just for name of the literature. But it's like the description is not much different. Then properties of these limits will depend on beta in some sense, this parameter. But so yes, it's a special example if you want, but of some very rich word indeed. Okay, but the first computation was really done in this case, and it's okay. We will see it in a moment. So beyond even thinking what is Brownian motion, that's not important. It's like for every t, yeah. So it's important, but not immediately. For every t, here I put, say there are functions, so for every t here I put a random number for each fixed t, okay? And so for each t, I will have t eigenvalues, n eigenvalues, sorry. But they depend on t now, and they are random, okay? So if we take it symmetric, again, so all independent except for the fact that they are symmetric, these endpoints will be on the line. And as time evolves, they evolve. Each of them moves a bit to the left and a bit to the right. And it's like this. And they keep oscillating and randomly. As we will see, they interact among them. So while the entries are independent, of course, the eigenvalues are not independent. They interact with each other. But there is a nice description on how they interact as a diffusion process, singular diffusion process. And as we will see, indeed, they repel each other. And okay, so there is this famous mean field description is called, which is due to Dyson, actually. So yes, let me recall you briefly then what is a Brownian motion. Okay, actually, they are just random variables in this space. Okay, so each of them is just a random function, continuous. Okay, in this space, so it's continuous. And there, what I put here is like before, of course I will put 1 over square root of n as we did before to normalize so that there is a limit. If you remember, these random variables were divided by square root of n. So if I fix each t, the limit of this object, I already know, okay, I will know the variance of this guy, which is actually t. So I already know the limit of this measure here as a function of t. But in this special Brownian case, I can have a much more explicit description and more like imaginative for each n, okay? They will be like n particles on a line with an interacting potential. So it comes like, they follow like a picture from statistical physics. That's for each fixed n. And then I can use this picture to compute in very deep detail all the features I want, for instance, in the limit of the largest eigenvalue or other, I don't know, sort of physical quantities, functionals, and so on coming from this description, which is like quite a powerful tool. So this answers your question, I hope. And yes, so let's make a very, very quick description of what is Brownian motion or a stochastic. So stochastic process, they have usually slightly more general description, but we will take just continuous stochastic processes. So it's just like for us, this is just a map from, say, a probability space, measurable map for a probability space, to the space of continuous functions, okay? With values in R. Or maybe, yeah, let's do in RD, okay? Then in the matrix, they will be in R, but it will be useful to make this in RD, okay? So, why Brownian motion is so popular, like in all classes, because like when you do stochastic process, there are different families of stochastic processes that people can study with different techniques, like, I don't know, Gaussian processes, martingale, Markov processes, processes with values in linear topological vector spaces, and so on. So Brownian motion, it's like in the intersection in all these guys. It's Gaussian, it's a martingale, it's a Markov process. You can have a description as a linear process, and so on. So it's no matter how you describe, you always fall on the same object. So Markov process, it's not. Is it clear what it means? No, it's okay. If you know, it's okay. So not a problem. So here it's good to use the description as both a martingale and the Markov process. So we will always think of continuous processes. So they take value in the space of continuous functions. Okay. So a martingale, B. Okay, taking values here, so this will be continuous. Martingale B is a stochastic process. Okay, is a map like this, B from omega to C0 infinity. So such a map, maybe I can say more. This map must be measurable, of course, and so okay, yeah, the definition is it would be slightly different, but I'm using effect. So first, it must have so a B like this is a martingale. If the expected value is finite, just to discuss what the expected value means, and if I take the expected value of b, so for each t bigger than s, if you give me the expected value of bt, so this is a random variable. Okay, you can think R each component for each component. Okay, given all the process up to time s. Okay. Then this is equal to Bs. So, let's make it, so you can give this definition for also times that are not necessarily zero infinity, but actually any ordered set. So here what it matters just that we can say it's bigger. So let's make an example with a discrete time. Okay, which is the easiest to understand. Like, I don't know, when is a sequence of random variables, b1, b2, bn, and so on, and martingales. Okay, the expected value must be finite, but like the expected value of bn given b1 up to bm, this should be equal to bm. It's like where I am at time n, if I know what I did from time 1 to time m. Like, even if you know what you did up to time m, it doesn't change the average of where you are at later times, okay? So where you are at time n is like where you were at time m plus something with average 0. An example, if I take independent random variables and I take bn, the sum of independent random variables, this will be with average 0. This will be a martingale, yes, because if I do the expected value of bn given, okay, if I tell you who is x1, x2 up to xm with m less than m, is the same doing the difference than giving you, they're giving you b1, b2, bm, so this means x1, xm, n is bigger than m, and this will be actually x1, so this will be, this is the sum, okay, to n. So this sum, let's write it as the sum up to n, xi, plus what remains, okay, so the sum from n plus 1 to n of the xi. So they are independent, so if you know the first term, these do not depend on this, so the expected value of this guy given x1, xm is just the expected value in this 0. But if I know x1, x2, xm, the expected value of the sum is just the sum, because I know it. So this is bm, okay? So here, in continuous time, it's the same thing. Like you have a curve on a linear space, so on R, it does something, okay? This curve changes over time randomly. But if you tell me who was the curve up to this time, the average of what it does later, even if I know what happened up to here, the average of what it does later is 0. Okay, so it's not just that the expected value, it's more than this. Then BT minus BS is 0. It's not just this, it's more than this. It's this even if you know what happened up to time s. No matter, this object, what it is a random variable that depends on all the path up to time s. Okay, it's some object that depends on this guy, what happened up to time s. So what I wonder is that the increase not only is average 0, but even once you know what happened up to time s, no matter what happened, you can see up to time s, the average will be 0. Okay. I don't know, we can make, if you have trouble with this, a simple example. I can flip a coin, yes, and then I just write twice. So if I can get a 0 or 1, okay, we probability 1/2. But my sequence is, or say I can get -1 or +1, we probability 1/2, better. And then I just write twice what I got in the first toss. Okay, so I write +-1 or I write +1 with the same probability. So this is a sequence of two random variables, x1, x2. This is not a martingale. Okay, even if the expected value so if they were independent, the sequence would be a martingale because the expected value of x2 is 0, even if I know x1, okay, if they were independent. But now x2 is actually equal to x1. So even if the expected value of x2, the second number I write, is 0. But once I know what happened up to time 1, the expected value is no more 0. Because if I know that it was -1, the expected value of the next is still -1. And if it was +1, the expected value is still +1. It's clear. So if they are independent, not only the expected value is 0, but they're really a martingale. But in this case, where I write twice the same number, x1, x2 is a sequence where x2 is actually equal to x1, that's not a martingale, even if the average was 0.
Okay. It means that so x1, x2 is a martingale, but bn defined here are not a martingale. Am I right?
No. Really, this sequence. I think both example works. Yes, because.
No, this is a martingale because this simply means that b2 equals to x2 equals to x1. Then this.
So the expected value. Oh, sorry. Yes. yes. Yeah, right. Sorry. And -2 + 2. Sorry. I made the only. Yeah, you are quite right. I'm sorry. Yes, absolutely. Thanks. So if I do here, if I take say -1, and the second number is just twice the first. So yes, thanks. So if I do here, in this case where I make a sequence x1, x2, when the first one I just throw randomly -1 or +1, probability 1/2. And the second one is just twice the first one. Okay? So if I know the first one, the expected value is to given x1 is twice x1. So it's not x1, it's not a martingale. x1 is 0 with probability 0, so it's not a martingale. Okay? But if they were independent, if instead I first I take -1 +1 with probability 1/2, and then independently I take -2 + 2 with probability 1/2, okay? Then this sequence x1, x2, this would be a martingale because the expected value of x2 given x1, oh no, and then I take indeed, sorry, yeah, you were quite right. I just thought this example to. So if I take then x1 + x2, this will be a martingale now. Sorry, but this is a sequence. This is so exactly what I wanted to give you was an example of a sequence where the increment also is 0 on average, but it's not a martingale. Yes, thanks. I just. Okay, so martingales are sort of a very powerful description of objects that fluctuate. If you have some random dynamics, or even actually deterministic, you can build some with, okay, you can build some martingales, and this is a way to describe the fluctuations of your dynamics. So in stochastic process or dynamical systems, they are quite a powerful tool because a lot of things are not about, they are very special objects. And okay, but let's stick on these, okay? On real numbers, when the time is a real number, positive maybe. And in this case, I can define what's called the quadratic variation of a martingale, okay? Let's to remember that it's quadratic. So the quadratic variation is again a stochastic process, so a map, again on continuous functions, and this is defined like this: the quadratic variation at time t. This is the supremum over all the partitions. So t1 equal to 0, maybe t0 equal to 0, t1 bigger than t0, up to the last time tn, which is the final time t, okay, of the sum from maybe 0 to n minus 1 of this function of the distance square, so here's just the square, of the function at time ti plus 1 minus the function at time ti squared. So if this would be these are continuous functions. Continuous functions, they are not that smooth. Yeah, they can be non-differentiable, of course. So if b would be if this guy would be differentiable, this I took the supremum, but I should have taken the supremum, but also the limit when say partition with ti plus 1 minus ti, say less than delta, and limit when delta goes to 0. So what I'm doing, I have like this part, okay? I'm dividing it in small chunks and just summing. So this is time, okay? This is what my part does over time. And I'm computing just these distances over little chunks of times and summing the square of the distances, okay? So if this path would be smooth, since it's continuous, these things will be small when the mesh is smaller and smaller. But if it would be smooth, okay, I could just sum not the squares and I would get the length of the path, okay? But so here I sum the squares, so they are much, much smaller. If the path would be smooth, like C1 for instance, this limit would be 0. Because if the sum is finite, like the length, the sum of the squares, each term is very small, it will be 0. Okay? But for martingales, so if a martingale is continuous martingale, as this sum without the square, which is non-zero, so say there is no such a martingale, continuous martingale. So maybe you can take other powers, not 2, or other functions, but say the idea is that these martingales will always have infinite length. Okay, so if I would sum to the power 1, this would be infinite for a typical martingale. Okay, unless constant, except constants. Which would be 0. So the typical thing is something like that, like it's continuous path, but really non-smooth in such a way that the typical martingale, yes, for which we are interested in, for which like the length of the curve is infinite, but this sort of length squared, so which is called the quadratic variation, is finite. So Brownian motion you can define a Brownian motion. So a stochastic process is a Brownian motion. It's not that there is one Brownian motion. It's like, I don't know, Gaussian random variable. Yes, you can build as many as you want with the same law. Brownian motion is the same. Yes, it's just a random variable with values not in R but in this linear space. So definition, okay, the Brownian motion is a martingale. So a stochastic process is a Brownian motion if, a stochastic process is a Brownian motion if it is a martingale with quadratic variation with, okay, expected value 0, with, let's say, b0 equals 0, b at time 0 equals 0. This is not so important. And the quadratic variation at time t is equal to t. So, this limit in theory is a random object, okay? But for Brownian motion, it's deterministic. So what does it mean? It's like we have a curve. Now this curve has like an infinite length. So you have to count the length in this quadratic sense, because otherwise you will always get infinity if you count the length in the usual sense, in the usual Riemannian sense when you make a mesh and sound the distances. But if you count with this square, it's sort of normalized in such a way that at time t, this sort of length is t. Okay, it's just you go through this curve with quadratic speed 1, and most importantly is a martingale. Okay, there are other characterizations that also interest us. So the point is that this property, there is only one probability measure on this space, which is the law of a Brownian motion. This is not apparent from this definition, but like so we have this map, yes, and we have this map from omega to C0 infinity. This is not clear from the definition, but this map, no matter who is your Brownian motion, its law, so the composition of the probability measure with the inverse of this map, will always be the same, and it's called the Wiener measure on this space. So I want to give another. So if I give a Brownian motion, I don't know who is the random variable. Of course, I can build it in 1 million different ways, but its law, its distribution, so the probability measure here will always be the same. It's not clear from this definition, but it's true. Okay, so another definition, which maybe you have seen, is the following definition of node 2. So you have just to trust me that all these coincide. It's not very hard to check it. So B is a Brownian motion if for all A1, AN in, say, R or RD if you want, measurable, and for all T1 bigger, so T1 smaller than T2, smaller than Tn, and also bigger than 0. The probability that B at time T1 is in A1, B at time Tn is in An. Still, I'm assuming that it's continuous. This is very important because I can make several probability measures on space of function with these distributions that are differ, and only one on continuous functions. And here they will be Gaussian. So the first, the integral will be in dx1 to dxn, and then there are all Gaussian distributions. So this will be, I start in 0, so x1 square over 2t1, then e to the minus x2 minus x1 square over 2t2 minus t1. So here will be like x1 minus 0 over t1 minus 0. And all Gaussians times exponential, all product times e to the minus x n minus x n minus 1. So these upstairs are the variables that I used to integrate over 2 tn minus 1. And then you know that you have to normalize Gaussian. So here there will be 2 pi to the n over 2. And then there will be tn. So t1, square root of t1, t2 minus t1. And so on and so forth, up to tn minus tn Okay, what does it mean? It means like that B at time t1, if you don't know anything else, t1 is the smallest time, is Gaussian with variance t1. Once you know t1, once you know x1, once you know where bt1 is, the next bt2 makes a Gaussian displacement with respect to t1 with variance t2 minus t1, and so on up to tn. So then you need to make a continuous curve. That's the interest. But if you just fix n values, t1, t2, tn, okay, you start in 1, then you want to, what is the, so how do you build B at time t1? Okay, you just toss a Gaussian random variable with variance t1. And that's where will be your bt1. So the probability that is in some set is just the probability that the Gaussian random variable is in that set. Then once you are here, to make the increment, you just toss a second Gaussian random variable with variance t2 minus t1 and centered in x1. So the increment is Gaussian with mean 0. Okay, so what is the probability that you are here? Is the probability that you are here and with a Gaussian random variable with this variance, you finish in this interval here. So this is time and this is our bt. So tac and tac. And then I go on up to time n. Every time I see where I am and I toss a Gaussian random variable with the variance equal to the interval of time. Okay? So then I can compute the probability that I start here, then I go here, then I go in this interval, then I go in this interval, then I go in this interval up to the last interval, and that will be this probability. Okay? It's clear that this is a martingale because once I'm here, the increment has averaged 0, conditionally even to where I am. Yes? So that's why it's a martingale. The way I build this is by construction a martingale. So this is the second definition. And it's not a completely trivial fact that you can build this in such a way that the curve, that you can realize this as a continuous curve. Okay, this is called the, okay, it's because I'm just giving you n points, yes? I could make a process with this feature, so a random function with this feature which is not continuous. And there is a unique way to do it up to probability 0 that I can do it with a continuous function. So the Brownian motion is the continuous function, like the random continuous function that has this feature. Okay? So.
Is there a way to prove that these two definitions coincide without using Fokker-Planck formalism? Because I don't know a way.
So this is a martingale is quite immediate, and that its variance, that is quadratic variation is t, so you can of course compute the variance on this t, and you can check that sum using this formula converges to a deterministic number. So once its value is t, you can compute the expected value of bt square, and this will be t. This is immediate from this formula because there is just one value t, so it's just a Gaussian random variable. But then you can compute also, from this it's a bit more laborious, but you can check that that this, okay, is actually deterministic.
No, so it's clear from the second definition to the first one. I don't understand the transition from the first definition to the second one.
There was no third definition. I gave two. One is the Brownian motion is a martingale, continuous martingale with quadratic variation t.
Yeah.
And the second is this, okay?
So the question is how to deduce from the first definition that, for example, ET is Gaussian.
Yeah.
I thought so. Okay. What I'm saying is from definition 2 to 1, it's easier. Okay, this is not, you can just compute it. From definition 1 to 2, that's Levy theorem. It's not, you need to do a bit of work. Can you avoid to pass through some Markov characterization?
Well, as I said, I know only about a way which uses Fokker-Planck formalism.
Yeah.
I guess that you can at least believe that this is true because when you know about quadratic variation, you say that when you take the sum of many infinitely small
Yes, yes.
If you're interested in the distribution of M, then it is more or less.
So exactly. So once you know that increments are independent, you get exactly this description, and indeed then you need to check that from the definition with quadratic variation you get independent increments, which I don't know. Maybe I think it's possible. Yes. In any case, also doing the long loop is not very long. And okay, let me give you the third definition. Probably it's a good time to stop then. So B is a. So I'm not very orthodox here. I'm a bit quick. But B is, so Brownian motion is a Markov process. So Markov process is like a stochastic process. There is not a unique definition. So this is more, but okay, let's call it Markov process with generator, one half the Laplacian. So this means just that for each for each function in the domain of the Laplacian, it's not for each. So this means that for each function in C2 with bounded derivatives of R, okay, f of bt minus f of b0, which is actually 0 for us, minus so this is 0, the integral between 0 and t of 1/2 the Laplacian of f of xs of bs in ds, this object, let's call it mf of t. So this is a martingale. Yeah, so for each, like, this is random, but it's a continuous function. So for each element of your probability space, if you want, you can compute f of bt. This is a function of continuous. If f is smooth, so this is a continuous function of t. This is a continuous function of t. F is C2, so this is a continuous function of S. I can make its integral, yes, and I get this random number for each function f. I get this real random number, which depends on t. Okay, so is this a martingale? So this is the expected value of mt equal to ms. So if yes, B is a Brownian motion. Okay, so why this is also equivalent to the other ones? Because so how do I build from this thing a probability measure on continuous functions? Okay, so first in the following way. So since this is a martingale, at time 0, this martingale at time 0 is just 0. Okay. So in particular, what I know that the expected value of f of bt is equal to, okay, the expected value of f of, yeah, let's do it for any. So yeah, okay, of f of b0 plus the integral between 0 and t of the expected value 1/2 of the Laplacian of f of xs in ds. Okay, so so you see this function bt, as you already understood from the definition of quadratic variation, it cannot be a smooth function. I cannot differentiate it. But if I take a function and the expected value, this will be a smooth function of t. So for each t, bt is not, so as a function of t, bt is not smooth, but expected value of it is smooth, okay? Because exactly, there are these fluctuations that in the expected value cancel out. So, so this tells me, so this is an inequality. So this tells me how changes in t the expected time of f of bt. Okay? Because it will be just 1/2 the expected value of the Laplacian of f in bt. So if I know, like, okay, so this allows me to build what's called a semigroup. So this allows me, so using the fact that I can use very, very little increment of times, okay, I can do the following. I can do exactly what we made before, like from B0, which, okay, we can take it equal to 0 or any point. You can start in any point you want. You can build BT plus the law of BT plus a very small error in T, and so on, BT1, BT2, and so on. So just from the fact that you know how the law, this tells me how the law of BT evolves. Because like for every function, I know the expected value of f of, okay, the derivative in T of the expected value of the law of BT. So if we call mu T, the law of BT, okay? This tells me that the integral dt of mu T of f is equal to mu T of delta f. So in this way, for instance, I can, for instance, this formula tells me immediately that mu T is actually Gaussian for every T. It's not enough to characterize the Brownian motion, but Gaussian distributions are the only one that satisfy this for every f. Then, so function depending on T. Yeah. So then I can, however, again do like mu Ts for s bigger than T, computing with the same technique the law of BT Bs, and so on. So to say, I can define STF in X, okay, from this formula, like the expected value of f in X plus BT. So if BT started in 0, I can build this this object, and from this fact, it will come that this operator on function is a semigroup in the sense that satisfies S st plus s is equal to st ss. Namely, if I take a function f, okay, if I compute s at time t plus s on f, I first compute the function SSF and then STF. Okay, and then how can I use this to build a probability measure on functions? I just so the Wiener measure, I can build it in the following way, up to the fact that it's continuous. So if you give me A1 like before AN, so measurable subset of R, I can build a probability measure. So by saying that the probability that BT1 is in A1, BTN is in AN, by doing so I should concatenate the semigroup, so I think it's clear. So first, if I do BT1, it's easy to do like this. In A1, this is just ST of 1A1. This should be, so when with B0 equal to 0, so in point 0. Because this is the probability that BT is in A1. So this is the expected value of the indicator function of BT1. Okay, so from that, like if I want to build a probability measure from the semigroup with keeping this property, okay, the only choice I can have to define it is this. Then I can do BT1 in A1 and BT2 in A2, and for this I have to do first, I evolve at time t2 minus t1, 1a1. I get a function, okay, and then I evolve it once I multiply by a, so a2, a1. And since I start, okay, compute it in point 0. And so on, I concatenate these. So here I will do s tn minus 1 indicator function of an multiply by an minus 1, apply the semigroup tn minus 1 minus tn minus 2, and so on. until st1, 1a1, to all apply to all the function coming on. So if you, it's again just why, like, for instance, for one time, I want to build a probability measure on the space of all functions, okay, continuous functions, that has this property, that this semigroup is the expected value with respect to this measure of f in bt, for x equals 0, okay? STF. So the only way I can do it is that if I want to characterize this measure by the probability of sets, at each time the probability that V1 is in A1 must be ST1 applied to the function, indicator function of A1. Otherwise, that property there cannot be true. Then I want to do it with 2 times, okay? So by using this, the semigroup property, there is only one choice that you can have for a probability measure on the space of all functions that satisfies the semigroup properties and this property at a fixed time, and this satisfies this one. And so on with 2 times, 3 times, with n times. So again, I am very fast because here, and I'm sorry if it's a bit confusing, just I don't want to prove you anything, yeah? Just to give you a bit an idea that like you can have at least, there are even many more, ways to characterize this process, and it's like just the picture I drew before for you, that f, like you start in here, then you do Gaussian increments independently every time. And this, if you fix a certain number of amount of times, if you fix a certain number of times, sorry, the probability that you are like in an interval at time 1, another interval at time 2, another interval at time 3, and so on, you can do it by concatenating successive tosses of Gaussian random variables. So the probability to do this is the probability, okay, that I don't know, you started in 0, that the Gaussian random variables with this variance is here, then that's the probability of being in the first interval. Then once you know where you are, let's say here, the probability that you finish in the second interval is the probability that the Gaussian random variable with this variance has an increment which falls from where you were in this interval. Then say that you finish here, the probability that you go here is the probability that the Gaussian random variable with this variance finishes in this interval, starting from here. So this increment is in this interval, and so on and so forth. If you build it in this way, okay, due to a well-known property of the Gaussian kernel that it solves the Hit equation, you will have this feature. Conversely, what I'm trying to convince you, this is a bit harder indeed, is that if you have this feature plus Markov property, so that this object is a semigroup, this property and this, you can go back to this measure. Okay, so I can start and build it like this. I can start and build it analytically with the semigroup associated to the Laplacian. So semigroup associated to the Laplacian just means that I have these semigroups acting on functions. Either if f is continuous, this is continuous. If f is bounded and measurable, this is bounded and measurable. And with this feature also. Okay, this means that the generator is the Laplacian. And the third has a martingale with quadratic variation t. So this will be a bit like we can use these 3 characterizations in the proofs. So I'm sorry that like I understand that it's a bit quick for 30 minutes introduction to stochastic processes, but just I hope to have given an idea why these things may be true. Like I can build, so what is the final thing you should retain? That I can build a probability measure on continuous functions from time 0 infinity to r or rd if I want, which is characterized by any of these 3 properties. First property, the resulting random variable, a random variable with this law is a martingale and has quadratic variation equal to t. Second property, it has this description that the probability that x at time x, this description, that if I fix n intervals in R and n times, I can write the probability that this random variable is at time t1 in the first interval, at time t2 in the second interval, at time t3 in the third interval, and so on, as the long integral as I wrote before, which is just corresponds to the idea that is the probability that when I start from 0, random variable with this variance finish here. Once I know that I finish it here in this point, say, is the probability that a random Gaussian random variable with this variance is in the interval, this interval minus this number. So like makes this increment, and so on and so forth, iterating each time. Second characterization. Third characterization, if I define expected value of f of xt, say for instance, fx plus bt, these semigroup on functions, okay, then so this is like if you give me a probability measure on C0 infinity, I can build this semigroup on functions, okay? And this probability measure will be the Wiener measure, so the law of the Brownian motion, if st plus s is stss, first property, and second property, dt, so this one, so dt mu, if you want, of stf is equal to mu of Laplacian of f for every probability measure mu and every smooth function f. Okay, so if you want the semigroup acts on the right on functions, to the left on measure, so mu t, which is the probability measure given, so mu characterized by mu t of f is mu of stf, is satisfies this equation equivalently. Okay, so since the solution to this equation is Gaussian, is given in terms of the Gaussian kernel, you can guess that this formula here, from this property, you can get this formula here for one time, for one step, for only one, the interval to finish in this interval. But this plus the semigroup property concatenates to build the measure we wrote before. Conversely, from the measure we wrote before, you can derive this formula and so on. So they are all equivalent. Again, I'm not proving anything, just trying to give you a very quick idea of Brownian motion. So, okay, it's a good point to stop. And yeah, sorry if the introduction of Brownian motion was a bit of a crash course, but okay, this is what we have.